Imagine you could tune a radio between stations, and instead of picking up music or talk shows, you detect an ancient whisper from the universe itself. That constant static, hissing in the background, is more than just noise. It's actually the oldest light in existence, still echoing across the cosmos. This is the story of the cosmic microwave background, or CMB, and how it changed our understanding of everything. Let's start with what the CMB actually is. Over 13 billion years ago, our universe was completely different. Hot, dense, and wildly energetic. There were no stars, planets, or even atoms the way we think of them today. Just a seething plasma of particles and light, so energetic that light couldn't travel freely at all. About 380,000 years after the Big Bang, something extraordinary happened. The universe cooled down enough for protons and electrons to combine into neutral atoms. Suddenly, the fog cleared. Light was finally free to travel, a moment often called recombination or decoupling. The waves of light released in this instant have kept moving ever since, stretching as the universe expands. Today, billions of years later, that same light still fills the cosmos. We call it the cosmic microwave background because it's not visible light anymore. The expansion of space over all that time has shifted it into the microwave part of the spectrum. With special detectors, scientists can see this faint glow coming from every direction, as if the entire universe were wrapped in a thin, cold blanket of ancient light. A poet might imagine this as the universe's memory. The CMB is a message from the deep past, written across the sky, inviting us to listen. Let's pause on that. What does it mean for the universe to have a memory? The CMB isn't just a backdrop, it's a fossil, a snapshot taken when the cosmos was young and unrecognizable. When we study it, we aren't just looking at light. We're literally looking back in time, peering into the universe's childhood. Every fluctuation, every minuscule ripple in the faint microwaves tells a story about the physics that shaped everything we now see. For a moment, imagine the sense of wonder the first scientists must have felt when they discovered this cosmic afterglow. In 1964, two radio astronomers working with an antenna intended for satellite communication stumbled across a hissing sound they couldn't explain. No matter where they pointed the antenna, night or day, there it was, pervasive, unyielding, and completely mysterious. This accidental discovery turned out to be the echo of the Big Bang itself, confirming for the first time that the universe really did have a hot, dense beginning. Let's reflect on that passage from Discovery. Sometimes, the most important clues about reality hide in everyday noise, waiting patiently for someone to listen. The faintest signals can overturn centuries of debate and illuminate mysteries we once thought unknowable. In this case, curiosity about a simple bit of radio static rewrote the story of cosmic origins. The existence of the cosmic microwave background is one of the most important pieces of observable evidence we have for the Big Bang theory. Before its detection, there were competing ideas. Maybe the universe had always existed in more or less the same state, or maybe it was operating in cycles. But the discovery of the CMB was like finding a photograph of the universe as a newborn. It was clear, striking evidence. The cosmos really did start out hot, dense, and full of energy, and has been expanding and cooling ever since. But what about the texture of this ancient light? The CMB isn't perfectly uniform. As we look more closely, we see tiny temperature variations, patterns that look random, but are anything but. These are the fingerprints of quantum fluctuations, stretched to cosmic scales. Where the CMB is denser or slightly warmer, it marks places where matter would eventually clump together under gravity. seeding the formation of galaxies, stars, planets, and ultimately, all life as we know it. There's a kind of poetry in this. The smallest quantum tremors in the earliest moments of time become the scaffolding for cosmic structure. The universe, in a sense, works like a giant amplifier, taking quantum jitters and turning them into galactic architecture. Let's pause to consider that transformation. What does it mean that the randomness of quantum fluctuations became the order of galaxies? In the everyday world, random noise disappears. Background chatter fades, waves flatten out. But in the universe, that ancient randomness wasn't erased. It was woven into the fabric of space-time itself. The trembling of nothingness became the foundation for everything. This brings us to another profound idea. When you look at the CMB, you're seeing not just the past, but the entire universe's potential. All across the sky, the CMB glows with almost perfect uniformity, yet tiny ripples encode the seeds of everything that would ever come to be. Stars, planets, galaxies, even us. Imagine reading a prophecy written in invisible ink, waiting only for the right kind of light to reveal its secrets. That's what the CMB is for cosmology, a prophecy, not just a relic. To understand how precise and delicate our measurements have become, consider this. The CMB's temperature today is just 2.7 degrees above absolute zero, almost unimaginably cold. Yet our instruments can detect differences in this chill as small as a few millionths of a degree. With each new generation of telescopes and satellites, like the COBE WMAP and Planck missions, scientists have created ever more detailed maps of these temperature fluctuations. Every pixel on these maps is a story. Microwaves that have traveled uninterrupted for almost 14 billion years, just to end their journey in our detectors. Let's pause to reflect on scale. Human senses can't feel a difference of a millionth of a degree, yet these minute measurements unravel the deepest puzzles of time and creation. It's a reminder of how technology extends our reach, letting us see, feel, and understand things far beyond what our natural senses evolved to handle. What can the CMB teach us about the universe's future? Because it records the earliest conditions, it also places limits on what's possible. Imagine trying to reconstruct the shape of a tree from a single seed. You'd know a lot about what's likely, but not every branch and leaf. In the same way, the patterns in the CMB set boundaries for how structures in the universe could have evolved. They even help us test ideas about dark matter, dark energy, and the ultimate fate of the cosmos itself. In poetry and philosophy, people have often wondered if the universe is knowable, a riddle, a mystery, or a code. The CMB offers an unusual reply. The universe, at least in part, left us a message in plain sight, waiting for us to develop the senses to read it. Its meaning is not something hidden in metaphor or abstraction, but written in the universal language of physics, temperature, vibration, and pattern. Let's pause and reflect, using the words of a poet who once said, "We are made of star stuff." If that's true, then we're also made of the memory light that reveals the story of stars themselves, a story that begins with the CMB. Gaze up at the sky, and you might see nothing but darkness. Tune your senses, and you discover the universe is still glowing with the memory of its own birth. So, what does this all mean for our place in the cosmos? The CMB invites us to adopt a cosmic perspective. We are not separate, not lost, but deeply and inextricably connected to the universe's own history. The very atoms in our bodies were assembled in places seeded by those early fluctuations. The light we study is the same light that shaped our fate, countless eons before the Earth itself formed. We might think of the cosmic microwave background as a kind of scripture, not in a religious sense, but as a foundational text inscribed on the cosmos, holding truths about where everything came from. It transcends cultures, languages, and beliefs, standing as a universal message for those with the curiosity and ingenuity to interpret it. But as fascinating as the CMB is, it leaves us with questions too. If this ancient light is everywhere, why can't we see it with our eyes? The answer is both simple and profound. It's there, but its wavelengths are now stretched far beyond the reach of normal vision. Only our specially designed instruments can glimpse this background hum, and even then, they must be cooled and protected from earthly noise. It's only through effort, patience, and technological innovation that this light becomes real to us. Think of it this way. The universe hides its most important clues, not in the bright beacons of stars or the violent outbursts of galaxies, but in the faintest echo of its own beginnings. To hear it, we must listen with both humility and precision, accepting what the cosmos offers and learning to ask new questions with every answer. So next time you see static on a TV or hear a whisper of noise on a radio, remember, a tiny piece of that signal just might be an ancient photon, older than the Earth, whispering its story from the moment the cosmos first became transparent. That's the cosmic microwave background, a silent witness, a cosmic memory, and a blueprint for everything that would ever come to be. Reflecting on the CMB, we realize that to understand our universe is, in a sense, to understand ourselves. In chasing the afterglow of creation, we're not just solving distant cosmic puzzles. We're tracing the origins of everything familiar. Every discovery brings us closer to answering humanity's oldest question: where did we come from? And what story does the universe tell about itself? The next time you gaze into the night sky, try to imagine an invisible glow, stretching in all directions, connecting past and present. An ancient light, always there, just waiting to be heard.